Well, hello and welcome back to Engineering 211 Statics. And we'd left off last time talking about trusses, and I wanted to continue on at that point. We'd introduced the concept of trusses, some of the assumptions, and things like that. And we started with a rather simple truss using method of joint. So I wanted to talk more about method of joints today. We'd also talked a little bit about zero force members, so I wanted to start at that particular point, talk a little bit about zero force members, and then get into a kind of an involved problem with method of joints. This is actually a picture I took when I was snowmobiling or snow machining, I think is what people normally call it that are in the sport, down by Diamond Lake, which is just a little bit north of Crater Lake. And they get a lot of snow down there, and these mobile homes or trailer houses or whatever you want to call them aren't up to supporting that load. So someone had built this structure over it, which is kind of interesting. The way this worked is there was bearing on this outside wall here, and there was bearing on this outside wall here. And it's not that great a picture. It's kind of late in the day. It was a little bit dark, and then I've blown it up quite a bit for it to be seen here. But I think the lesson is still good. So this truss was built, and it was supported on this outside wall and that outside wall, and then of course the walls were supported down below. So the game plan was to try and get the snow load to either slide off or be supported on these outside walls so it didn't collapse the roof. Well, I think there's some zero force members in here, so let's see if we can find those. Let's make a little more careful diagram of this, and we'll have something like this, and we'd have these reactions over here like this. Maybe we'd have a horizontal one there, and then what do I have for the webs? I've got the top chord, I've got the bottom chord, and then I've got these webs in here. Sometimes we call it the king post, and then these are sometimes the queen post over there. So like that. And it's hard to see from the pictures, but there's no load on the bottom and there's no reaction on the bottom. So there's nothing touching there, but we'd of course have snow load, and we'd put that snow load at these joints like that. That would cover the dead load of the structure itself, the metal roof, and then the snow load that is probably going to pile up. Even on a roof this steep in that region, they'll get some snow piling up on it. So we'd have something like that. Well, if we were to come over and look at a Freebody diagram, maybe of that point right there, that diagram might look like this. We might have tension in the bottom chord, and then if we have this member here coming in, if we look at that, if we look at summing the forces in the vertical direction there, this one has to be equal to 0, doesn't it? Now, we could resolve this one the same way, so we'd recognize that's a zero force member and that's a zero force member. Now, if we go up here and start to look at maybe is this a zero force member? No, because if we look at doing a Freebody diagram at this joint, maybe right there, what are we going to have? We'd probably have compression in the top chord like that. We'd have this load coming down like that, and then we're probably going to have some sort of compression in this member there. So that would not be zero force, and that would not be zero force. But these two little posts here, this one right here and that one right there, are zero force members. If you look at the way these things are usually done, and had there been a load here, if someone had come in and put some load there, or maybe they had some reaction there, then there would be definitely a purpose for that. Maybe if we had thought about how this was transported to the side, or were concerned about reverse loading or something, maybe in a windstorm or something, maybe those would make sense. But I don't think we could justify those with any of those. I think those are just simply zero force members, and people probably got together and thought that looked like a nice truss and went for it, and they didn't realize those were zero force members. What might be a better design for this is to look at a truss that looks like this. If you have a house that's been built since the about the 1975 or so, there's a pretty good chance it has a truss roof, and you crawl up in the attic and look at that. They're probably not going to use this arrangement. They're going to use something that looks like this, okay, and they'll have more efficient member distribution, less zero force members and so forth. So let's try and quantify this. I've done this before. Let's maybe use a few more numbers on this so that you can recognize these. The other thing is the zero force members. You probably want to try and be able to recognize them right off because it'll make your life easier. You go through the problems faster. But if you miss one and you get to this point and you're honest with your calculations will show that it's 0. Let me show you a couple cases that come up that lead you to zero force members. So let's take something like this, maybe where I have a couple of members here. And so maybe we've got F. Let me see exactly how I want to do this. Yeah, I can say I have F1 and F2, and then maybe I will put F3 into this thing. Maybe I'll define this. We'll say that this is a right angle here, so we'll say we've got theta. So if I rotate my coordinate system and I come around here and I look at a x, y coordinate system, if I talk about summing the forces in the y direction, setting those equal to 0, essentially doing a moment of joints at this pin connection here, I would have what, F3 times, that's not a very good 3, I would have F3 times what? The cosine of theta. Anything else? Well, these are perpendicular to that. Those are strictly in the x direction. So I get that, don't I? And what do I recognize? That F3 has to be equal to 0, doesn't it? Okay, that F3 has to be equal to 0. Only way that this would not be, only way we get the 0 out of the cosine is if we had what this laid down over here and we got 90, isn't cosine of 90, 0, yeah. So as long as this theta is not 90 degrees, as long as this is not rotated down here and in that direction, this cosine is not going to be a factor, so F3 has to be equal to 0. Now another case that we run into sometimes is probably worth putting up here too, and maybe this is even a little easier case than what we just handled right there. Let's say that we have something like this, and then we have another member like this. We'll say that we have F1 here and F2 there, and we could talk about this being equal to theta. Maybe take again an x and a y coordinate system. If I sum the forces in the y direction, setting that equal to 0, what do I have? I have, maybe I better give myself enough room to deal with this. I would have that 0 would be equal to what's going on in the y direction, minus F1 minus F1 plus F2 times the sine of theta. Okay, we don't get much from that. That has both of them in there. But what if I go the sum of the forces in the x direction, setting that equal to 0? We have 0 then is equal to, this F1 is not in the x direction, it's all in the y direction, and all I have is F2 times the cosine of theta. That technically would be negative, probably taking a positive to the right, so I'd have minus F2 times the cosine of theta. And again, F2 would have to be equal to 0. So if you get F2 is equal to 0 and you come back and you put that into there, then F1 has to be equal to 0. Which makes sense, because I think if you didn't have any other forces, I mean, all bets are off. If we have a force over here like that, I don't want to get too carried away with that, but if we have a force going like that, then all bets are off on this if we have a load or reaction there. But if we don't have that, if that's not there, you could imagine that if there's nothing resisting F1 and F2, that this point is going to try and move in that direction, isn't it? So a couple of things to keep in mind as we look at those situations. Well, let's try a problem like this. So we've got a nice little truss problem here. I have 3 loads on this. I have a vertical load at B, that's 1 kip. I have a horizontal load at C, that's 1 kip, and I have another vertical load down at E, that's 1 kip. And kip is a unit. The structural people, they deal with lots of large loads. They don't want to have to keep track of pounds, so they say that 1,000 pounds is equal to 1 kip. So a kip is just 1,000 pounds. So let's say that I want to try and find the force in BE. That's right there. So I think what our scheme is going to be is to find my reactions at A, then probably do a free body diagram at A, and then a free body diagram at B, and maybe I'll have to do one at F, and hopefully I can find what BE is. So let's do that. If I start out here and I draw this free body diagram of this thing, and this is back to Chapter 5 material. I'm not going to worry about the individual truss members and whatnot. I'm just going to kind of put that in a black box. I'm going to say that I have 1 kip there, 1 kip there, and 1 kip there. With the roller at D, I'll say that I have R3 here, and with the pin at A, I'm going to say that I have R1 here and R2. So R2 is the vertical support at A, R1 is the horizontal support at A. And we'll note the dimensions here. Each one of these panels, that is the dimension from A to F, is 10 feet, F to E is 10 feet, and E to D is 10 feet, and then this thing is 10 feet high. So these angles in here would be 45 degrees. So what I'm going to do then is I'm going to sum the moments about this point here, A. So summing the moments about A, setting that equal to 0, I get 1 kip times, I mean, this force is times what, 10 feet? So I have 1 kip times 10 feet plus, so it looks like I'm taking clockwise as positive, plus 1 kip times this total distance here is 20 feet, plus then I have this this one here, it's acting along that line, which is 10 feet, plus 1 times 10, and then I'm going to have to subtract off R3. I don't have to worry about R1 and R2 because they intersect A, but I will subtract off R3 times the distance it acts through, which is 10, 20, and 30. So I can say then that R3 is equal to what? 10, 20 is 30, and another 10 is 40, divided by 30, which gives me then that R3 is equal to 4/3 of a kip. Okay, so that worked out okay. Well, let me continue on then. The sum of the forces then in the horizontal direction, setting that equal to 0, what do I have? I have R1, so I'll go ahead and take that positive to the right, and I have the only other horizontal force is this 1 kip, so plus 1 kip. When I solve that equation, I get that R1 is equal to minus 1 kip. Okay, so we've got this one, we've got that one. A lot of you probably, when I put this R1 down, might have said, well, hey, how can you have all of your horizontal forces? That was this one and that's that one going to the right. It's going to start to accelerate to the right. Since we don't want it to accelerate to the right till we get into dynamics next term, we had better come up with R1 being opposites. So that's where that negative sign comes from, indicating that I assumed the wrong direction for R1, and it's really the opposite way. Instead of to the right, it's to the left. Well, let me finish up then with summing the forces in the vertical direction, setting that equal to 0. I'll go ahead and take positive up on this, and we will have R2 plus R3. That's pushing up, and then I have minus 1 kip minus 1 kip. And let's see, that's horizontal, that's down, those two are up. So I make my substitution for R3, that's 4/3. And I can say then that R2 is going to be equal to 2 minus 4/3, which is what, 6/3 minus 4/3 gives me that R2 is 2/3 of a kip. Okay, so this was again Chapter 5 material, equilibrium material. No truss work yet, no structural work yet. And the reason I say that is because you've got to do these, and you've got to get these right. Our answer is going to depend heavily on R1 and R2 as we go along. So it's very important that you get those. Well, let me keep up with the page numbers. This was page 2. This is page 3. So let me grab another one of these. We'll say this is page 4. And I'll put my reactions here. So this one turns out to be, where's R2? 2/3 of a kip. This D is R3, which is 4/3. And I think I'll go ahead, I've drawn R1 to the right here. It was negative, so I think maybe for this one here, I'll turn it around and say that I have 1 kip. Okay? Or I could, if I wanted to, draw it to the right and call it a -1. So I put those reactions on here, and I've really just done this, but if you're working on your engineering paper, you don't have the space constraints necessarily that I do. You would just keep going with this. But I'm going to have to move on to another piece of paper. So if you'll allow me to do that, I'll start page 4 here. So we've got our reactions. Getting the reactions is very important. And now that I have that, I could go ahead and look at maybe a Freebody diagram at pin A. So pin A. So what do I have going at pin A? Well, I have this 1 kip there. Again, that was a negative value, so I turned it around, called it positive. Then I've got 2/3 kip like that. And then over here, oftentimes, like I mentioned last time, this is the bottom chord. Okay, and this is the top chord. A lot of times the bottom chord, not always, but a lot of times we have tension. So I'm going to say that AF, and I usually write those alphabetical, AF is in tension. I'll draw that in tension. It's leaving that point. A lot of times students have trouble seeing whether something's tension or not, so that's maybe worth spending a little bit of time on. I'll back up and use a little clear piece of paper here. So when you have the pin here and you draw a force like this, that's actually tension, isn't it? Because if we were to look at the member that would be holding that pin would be going through, by Newton's third law, equal and opposite, that force has to be like that. And hopefully that makes sense that that's tension. Conversely, if we were to draw a point like this and have the force going like that, that's compression, isn't it? And if I were to look at the member that has that the pin goes through, by equal and opposite, we have something like that. Okay, so this is tension, that's compression. A lot of times people have trouble getting a hold of that. Well, anyway, I've got AF drawn in tension. I've got AB, I'm going to draw that in compression. So there is AB. This is going to be, of course, 45 degrees based on our geometry. Do I have any loads? I've got the reactions. I've got that one. I've got that one. I don't have any loads on that node. So I think we're good to go there. We should be able to do this because I just have 2 unknowns. So let me then sum the forces in the vertical direction, setting that equal to 0. So in the vertical direction, I have 2/3, because that's going up. And then I'm going to have to subtract off the vertical portion of this, which is AB times, what, √2/2. So they're always fighting about whether it's cosine or sine of 45. I'll just say √2/2, it's the same value. So we know that's equal to 0, so I can say then that AB is equal to what? Moving that to the other side, I get rid of the negative sign, and I'm going to then have 2/3, and I'll have to multiply this by 2 over square root of 2. Forgive me for having the radical in the bottom. We'll say that this is 4 divided by 3 root 2. Which is 0.943 kips, and it's positive. Okay, so if I had to, we're really looking for the force in BE. We're looking for the force in that one. So I don't necessarily know that I need to answer AB, but if I wanted to answer AB, I could say, so therefore, I think you're getting this on your screen there, yeah, that AB is equal to 0.943 kips, and because it's positive, I drew it in compression. It will have to be compression, isn't it? Okay, so that would be a proper answer. Okay. So we answered what the magnitude was and whether it's in tension or compression. Now, while we're here, we could look at AF if we wanted to. We could sum the forces in the horizontal direction, setting those equal to 0. And what would I have? I'd have, we'll take to the right as positive, so I would have AF minus 1 kip, and then minus AB times the 2 over 2, right? So I can say that AF is equal to 1 plus AB, 0.943 times root 2 over 2. So AF turns out to be equal to 1.67. Now that's positive 1.67. So how do we draw AF? We drew it in tension. So I could say then that AF was equal to 1.67 kips in tension. Okay. Now, we didn't necessarily need AF. We desperately needed AB. But as we'll come back and work this problem when we get to method of sections. It might be nice to have AF. So we'll come back to this. But let's then go do a Freebody diagram at pin B. So at pin B, what do we have? Well, there's pin B. So I'm going to have AB going in there, aren't I? This is AB, which we just found was what? AB was 0.943 in compression. So 0.943. It's in compression. I've drawn it in compression, so we're good with that. Then we have this BF. So I'll say that I have BF. And then I've got this BE. And then I've got BC. And let's see, BF, I really didn't know which way that was, so I just assumed it was in tension. I may or may not be right. BE, again, I just assumed it in tension. I may or may not be right. We look at some geometry. We've got 45 and 45 and 45. The last thing, we don't want to forget this load. Sometimes it's easy to forget the load, so I've got to go ahead and place the load on there. There's 1 kip. Okay. Now I have a problem with this. I have 1, 2, 3 unknowns. Okay, I have a problem, 3 unknowns. So what am I going to have to do? Well, I'm going to have to go over here and take a side and do a free body diagram at F. Or pin F, if you will. And I'm going to have something that looks like this. I've got this AF, which we actually found. We found it to be in tension, so I'll draw that in tension. There's AF. And then I'll have EF. And then I will have this BF. And so it's in tension, so there is BF. Happens to be a right angle. And if I sum the forces in the vertical direction there, setting it equal to 0, what do I have? BF is equal to 0. We actually have a zero force member here, don't we? Because there was no load at this point, no downward load there, we have a zero force member. So some of you may have recognized that from the beginning, which would have been kind of nice, would have saved us this work here. But if we didn't, and then we're honest, we don't try and guess something or force something that it's not, this comes out, this is 0. And now I have only two unknowns. Now what if I'd drawn the free body diagram in pin B? I mean, after all, we were looking for the force in BE. We might have been tempted to draw B first. AB would have been an unknown, so I would have had 1, 2, 3, 4 unknowns, and then I would have taken care of this, so I'd still be left with 3 unknowns, and then I would have had to have gone back over here. So sometimes when you have too many unknowns, you have to go do another point and then come back. Well, with this one, let's sum the forces in the vertical here. Setting those equal to 0, what do I have? I've got AB, which is 0.943 times root 2 over 2. I'll go ahead and take positive up. So that's that one. And then I'm going to be subtracting BE times the square root of 2 over 2. That's that one going down. This is 0. So then I'll just have to subtract off that 1. So I've taken care of this one. I've taken care of that one. I've taken care of that one. This one is 0, and that one's horizontal. So I should be able to say that what BE is equal to, let's see, move that to the other side, it becomes positive. So I have 9.4, whoops, not 9.4, 0.943 times the square root of 2 over 2, that's that piece, minus 1, and then what do I have to do with that whole thing? I'm going to be multiplying it by 2 over the square root of 2. So when you run the numbers on that, you end up with, let me double check what I got in my calcs, minus 0.471 kips, which if we wanted to talk about BE, that's what we're actually really looking for. So we could say, therefore, that BE was equal to 0.471 kips. You might choose to say 471 pounds. I'm going to keep it in kips because we started in kips, everything else is in kips. But this negative sign, how was BE drawn? BE was drawn in tension. So this negative sign means that it is what? The opposite of tension. What's the opposite of tension? It is compression. So the preferred answer is going to be to say that it's 0.471 kips in compression. Now some people might say, well, I'm going to leave the negative, minus 0.471 kips in tension. That's a little confusing. That's like saying, you know, we're not going to have school on Monday, which really means what? We're going to have school on Monday. So I usually at this point, I leave this. I think this is an important part of the calculation because it matches up with our free body diagram. But in my final analysis, my final statement, I deal with that negative sign and take care of that in terms of tension or compression. So we answered that problem. While we're here, we've got one more. I think I'll do BC because, like I said, we're going to come back and tackle this problem again with a different methodology. So let me sum, see if I can fit these all in here. Sum the forces in the, we did vertical, so I'll do horizontal, setting that equal to 0. We'll go ahead and take positive to the right. And what do I have there? I've got probably, let's see, I've got several terms, so I'm going to start over here. I'll say that 0 is equal to 0.943 root 2 over 2. That's the horizontal portion of that. That's positive. Minus BC. So I've taken care of this one. I've taken care of that one. Those two are vertical, and that's 0. So all I have to do is add to it plus BE root 2 over 2. So that's equal to 0. Do I have a substitution for BE? Yes. Now, I took BE going to the right as we had indicated it up here in tension. So when I make the substitution, I had better substitute what into here? I'd better substitute a minus 0.471. Okay? Because the way this arrow was drawn, the answer is negative. So when I then find BC, I can say that BC is going to be equal to, what will that be? I can factor out a root 2 over 2, and then I have 0.943 and minus, is that right? Yes, 0.471. So BC is equal to, I run those numbers, as I get 0.3338, I'll call it 4. It's probably a third, probably that we've got some round off going from this 0.943 and so forth. So hopefully I've got enough room here. I can say then, therefore, if we wanted to, BC is equal to 0.334 kips. It's a positive number. I drew BC how in compression, so it would be compression. Okay, so let me double check these with my notes for you. We've got BC 0.334 kips in compression. We've got BE, that's 0.471 kips in compression. What did I have for these? AB 0.943 kip, and that was yeah, that's compression, and AF 1.67 kips, and that would be tension. So we answered the question here. We did quite a bit more work than we needed to, because like I said, I'm going to come back and try this with a little different method and see how this works. But these problems, you can see, they're usually not very difficult, but they can be tedious. They can be a lot of spots where you can make mistakes as you go through them. You might ask yourself, is there a way that we could have got to this a little faster? Well, you could try if you wanted to and start with D and work your way over there. Go from D to E. I think you're probably going to have to go D to C and then to E, so you can try that. You should get the exact same answers. That'd be a good exercise. The next way that we're going to do it, so I'm going to grab another one of these sheets here. So this will be our last sheet for the day, or the lecture, is with method of sections. With method of sections, what we're going to do is we're just going to section through that thing. So we'll cut this apart and essentially have something that looks like this. Have a reaction there and reaction here. We've got a load there. And then I can't just cut it apart. I've got to replace that, severing those members with some forces. So I'll say that I have this force, and then maybe this force here, and then this force here. And over here, if we were to look at it, and usually we'll just look at one side, but if we wanted to look at both sides, what would you have? We'd have something like this, and then something like this, and something like that, and we'd have this piece over here, and we'd have to make sure we put the loads on it. There's that load, and this load right there. So 1 kip, 1 kip, 1 kip. These are reactions. This is our reactions here, here, and there. So you could imagine if you then slide these back together, these forces cancel out, and you get what you started with. The nice thing about this then is if I come back and maybe look at this side here, I can find that one directly. So it's going to be a little faster if we're looking for the force in one particular member. If we're looking for the force in all of the members like we do sometimes, I'm not sure it's any faster than method of joints. Well, that's what we'll do when we come back next time. We'll look at method of sections and work on method of sections, and we will go from there. So take care till then, and thank you for watching.